Hello, Chem 1B, and welcome. This is going to be our first chapter, chapter 14, and this is lecture video 1. Chapter 14 is all about chemical kinetics, which is really just the study of how quickly chemical reactions will occur and what affects the rate of reaction and how quickly it happens. Now, some topics that you should probably have reviewed are molarity is a big deal here. You need to know how to calculate it. I'm not going to go over it. That's something that was covered in Chem 1A. In addition, stoichiometry, balancing chemical equations, all of these things are prerequisite information to this class, really, as well as naming. So chemical kinetics is a pretty neat field. I myself did quite a bit of research in this field. So a lot of laser technology can be used to measure fast-changing reactions. Reactions that give off a lot of energy often are very quick, like explosions are always very fast reactions. So let's talk about chemical kinetics. So if we think about that, what are the two most important questions to ask about a chemical reaction? Now, they are really, the first one is, will it happen? In Chem 1A, you learn to kind of predict whether or not an aqueous reaction will happen based on whether it forms a precipitate or a non-electrolyte or a weak electrolyte or a gas. Knowing whether the reaction will occur is kind of an important thing, right? Because otherwise, why waste any time studying it? Now, will it occur is the first question. The second question that's very important is how long will it take? If we don't know how quick the reaction occurs, it could be very dangerous. Like I said, very, very fast reactions that release a lot of energy can be explosive. Or it could be very kind of disappointing, right? We don't see anything happening over a short time scale. And that could mean other things that we need to take into account. Now, will the reaction will happen? That's really based on thermodynamics, right? Is the reaction energetically favored? Now, we're going to be able to learn a lot more about this in a later chapter in the class. We already learned something about thermodynamics in Chem 1A with enthalpy and all that. That we're not really going to talk too much about in this chapter. Kinetics really is our main deal here. And kinetics is going to be, hey, how quickly does this reaction happen? Now, if we look at this, this is what we call an energy or a reaction coordinate diagram or energy diagram. Now, this diagram shows, hey, we have our reactants here. This is like kind of our starting point. And in order to get to our products, we need to have enough energy to climb up over this barrier here. Now, this barrier is what's known as the activation energy barrier. And it really has a big influence on how quickly this reaction happens, right? If this barrier is really big, then less of our reactants are going to have enough energy to get over it. And that doesn't mean they won't. It just means the reaction will happen much slower. Whereas if this is a really small reaction barrier, like something like that, well, we're going to have a much faster reaction if this activation energy barrier is smaller. This barrier is what really controls how quickly the reaction is going to occur because of that. Now down below, this difference in energy between the reactants and the products, this is really our thermodynamic side of stuff. Cool, so let's continue on. We'll talk more about reaction coordinate energy diagrams later. Kinetics is really the study of how quickly these reactions are going to occur, any reaction. And there are really 4 important factors that are going to affect how fast our reaction occurs. Now, one of them is temperature. And we'll learn more about this later, but effectively, the higher your temperature, the faster your reaction will happen as a general statement. The second is reaction concentration. The more reactants we have present, the quicker our reaction will occur. We'll find out. And this makes hopefully a lot of sense because the more of them are present, the more they can collide or react with each other to form products. With really low concentration, you're going to find that it's harder for our two reactants to kind of meet up in order to react, right? Even in an aqueous environment, if our reactants are in really low concentration, that means there's not very many of them within the solution, and they need to kind of meet each other in the solution in order to react with each other. So the higher your concentration, the more likely that will occur, and the faster your reaction will happen. For solid reactants, really what matters most is surface area. We're really not going to focus on solid reactants for the most part in this chapter. This is the only time I'll talk about this. So let's talk about the fourth and final one, and that is the action of catalysts. Catalysts, what they primarily do is they lower the activation energy barrier, which, like I said on the previous slide, really affects our rates of reaction. So these are the four things that we kind of are concerned with. We're going to mainly be focusing on these three in this class. And if I'm being completely honest, we focus on these two here, temperature and reactant concentration, more than anything else. So a rate is really the speed, how fast something changes, but specifically always with respect to time. So think about like the velocity of your car. We typically in the United States measure our rate of speed in a car in miles per hour. The per hour there is the respect to time, right? How many miles did you go? Cool, that's 50. Great, but how many miles did you go per unit of time? Well, in per hours, maybe it took me 2 hours to go 50 miles. Well, then I was going 25 miles an hour. For a reaction A, let's say that's our reactant, going to B, our products, the average rate of formation of B, because products, we form products, right, would be simply the change in our concentration of B over the change in time. Now, often we use a symbol like this to represent this, right? Delta, we learned in Chem 1A, means change in. And change in always pretty much means final minus initial. So if we want to talk about this symbol here, we have delta concentration, the brackets, that indicates a concentration unit. So specifically, we're talking about the concentration of B, and the change in it in the numerator. Well, that's really just the final concentration of B after the reaction is stopped or after a certain amount of time, minus the initial concentration of B. And this is all over delta T, which again, change in time then. So T final minus T initial. All right, so let's continue on. So we collect some data for a reaction. Specifically, we look at the concentrations of one of the products and one of the reactants, right? So we have this guy's concentration and we have this guy's concentration versus time. Now, over at time 0, we have initially 1 molar of concentration and 0 molar of concentration of these two things, respectively, right? The reactant at 1 molar, haven't used any of it at time 0 yet. Therefore, at time 0, we haven't formed any of our products yet. But after 20 minutes, our concentration of tert butyl chloride, or C4H9Cl, has gone down, and our concentration of tertiary butanol has gone up. You don't need to know the names of these organic compounds yet. And this continues, right? The reactant concentration continues to go down. The product concentration continues to go up. What is the average rate of formation? Formation is an important word here. It means we're talking about a product for the most part. And that means our average rate is going to be positive. So if we look at this, what is the average rate of the formation of tertiary butanol? Well, let's do T0 to T20, right? So our delta concentration of C4H9OH all over delta T would simply be equal to our our concentration final, which is 0.46 molar minus 0 molar, all over our T final, which is 20 minutes minus 0 minutes. Now, if we look at these two, right, we can calculate that. We're subtracting 0 off the numerator and the denominator, really. So this is really just 0.46 divided by 20. And this will give me a rate of 0.023 molarity per minute. Now this could be our average rate of formation. All right, like I did on the previous slide. Now, but there was a couple other values in that data table. Why did I choose 0 to 20? If I chose 0 to 40, would it have been different? Or if I chose 20 to 40 minutes time frame, would I have gotten a different value? It's very likely that we would have gotten different values, and they all would have been correct technically. Now, like I said earlier, because this is a product, the rate is going to be positive. So if we looked at 0 to 40 minutes, that rate, looking up those data values in the table, we would get a rate of 0.0175 molarity per minute. And if we did it from 20 to 40 minutes, we would have got 0.012 molarity per minute. Now, these three values here, this one, and this one, are all different from each other. This is because we are calculating what we call an average rate, and our rate of our reaction actually changes over time. Specifically, most of the time, it gets slower. As time goes on, the reaction slows down generally. And so all of these values are technically the correct answer, just over a different range of time. This one was between 0 and 20 minutes. This one was between 0 and 40 minutes. And this one is between 20 and 40 minutes. So which one's correct? The answer is all of these are correct over different time periods. Now, average rate, because of that, isn't all that useful because it changes so much if you just average over a different time frame. It's not as good of an indicator of the reaction rate. Looking at an average rate and comparing it to another reaction's average rate, you wouldn't be able to determine very much information from that. Generally, what we really want is what's known as the instantaneous rate. Now, the instantaneous rate is, instead of over a range of time, we're really to determine what the rate is at a given instant in time, right? So not between 0 and 20 minutes, but hey, at exactly 15 minutes, what's the rate at that instant in time? That would be an instantaneous rate. There is a special instantaneous rate, which is known as the initial rate, and it's the one that's most desired. The initial rate of a reaction is the rate right when the reaction starts. So in other words, it's the instantaneous rate at time 0. This is going to give us the best rate in which we can compare to other reactions. So if we look at a graph of that same reaction that we talked about earlier, but this time we're looking at a graph over the concentration of that reactant versus time in seconds. All right, and as you can see, as the reaction progresses, the concentration of our reactant goes down, which hopefully makes a lot of sense. As the reactants react, they break down and form products, so the amount of them present is going to decrease over time. Because of this decrease in our reactant concentration, our rate of our reaction is going to slow down. Now, if we wanted to look at some average rates, we can go, hey, we're initially at 0.09 molar, then we go to 0.055 molar, and this took, well, basically about 250 seconds, right? Because this is probably about like 50, and then we got to 300. And we can calculate that rate of the reaction, but because it's between these two different times, it would be an average rate. Now, if you think about this, this is really just equal to the rise over run over that time period, right? In other words, the slope of this line at that average of time, right? In range of time. When you look at it differently, you can kind of see this slope here is much less steep than this one. And this is because it's happening over a much later time range, right? We're between 500 and 800 seconds here. The reaction has slowed down significantly between these two different ranges of time. All that's great, but that's not what we really want to talk about. We want to talk about the instantaneous rate. Now, what's different about the instantaneous rate? What do we do differently? Well, an instantaneous rate is going to be the rate at a single instant in time, like I said earlier. Now, how do we figure that out? Now, what we do is, let's say I want to take the instantaneous rate at exactly 600 seconds. I want to know how fast this reaction is happening right when we're at 600 seconds of elapsed time. Now, what we do is we figure out the equation of this line, the red line, and then we would plot the tangent line to that point at 600 seconds. We would evaluate the tangent line to determine its slope. We want the slope of the tangent line. That is going to equal our instantaneous rate. Now, if you've taken calculus, you know there is a very easy way to determine the slope of the tangent line, and that is take the derivative of the curve that you are looking at. Now, calculus is not a prerequisite for this course, so I'm not going to be asking you to do that. But this is how we would determine it nonetheless. And you should have a kind of basic understanding of how we could get an instantaneous rate. I'm not actually going to ask you to calculate it using calculus. We have other ways of determining initial rates or instantaneous rates in the chapter that don't involve calculus, but you should kind of have an idea of where it comes from. Now, like I just said, initial rates are also important. The initial rate is just the instantaneous rate at time equals 0. In other words, if you've taken calculus, you know that we're now evaluating the derivative of this line at t equals 0, which would give us the tangent slope at time 0. It's kind of a neat thing. You can actually see where calculus starts to get involved in chemistry. And if you have to take, if you're a chemist, then you'll learn a lot more about calculus and chemistry once you hit physical chemistry, which is the classes that you'd take after organic chemistry. All right, so let's talk about an average rate problem, and then we'll finish off. So let's say we want to calculate the average rate of, now we're talking about disappearance of CH4 from 10 seconds to 20 seconds using this data table. Now, if we want to do this, what we need to do is we need to understand that, hey, I'm doing this over a time range, 20 and 10 to 20 seconds. So I'm really going to be using these rows here to do my calculation. I'm doing this for the reactant. So I know delta T over of C, or delta concentration of CH4 or C4H8, sorry, over delta T is equal to my rate, my average rate equation for this problem. Now, that is pretty simply just going to be, hey, what's my final concentration? It's 0.835 molar. What's my initial concentration? Hey, it's 0.913. And that is my numerator of this equation. This is that, right? T final minus T initial. My final concentration is at 20 seconds. My initial concentration is at 10. And then in the denominator, we have 20 seconds minus 10 seconds here. And if we plug that into our calculator and solve, we can get our average rate of C4H8 over this time range. And you're going to get that this is equal to negative 0.0078 molar per second. The negative sign is important here. It needs to be included as this is a rate of disappearance, meaning it's disappearing. So the rate is negative here, meaning that our concentration is going down at this rate. All right, so this is the end of this chapter. If you have any questions, please email me or come to the discussion sessions that I hold. See you there.